Hello everyone, welcome back to Advanced ANOVA Week, and this is part 2 of the video. So in part 1 we talked about all about ANOVA models, which are pretty cool and flexible models that you can use to understand change from pre-test to post-test and look for group differences according to categorical variables, which is pretty cool. So we looked at several examples of those. And in this part, we're actually going to start talking about repeated measures in ANOVA. So this again is in the Module 4 handout file. It's all the way down. We're starting down on line 116. I'm not sure what page it is on the handout, but pretty far down, maybe halfway through or so, with what I call example number 3. So repeated measures in ANOVA, and I again recommend the lecture video here as an example of this. It is a really useful tool for handling situations when you have more than 2 occasions of measurement and you want to understand if there has been change over time. If you only have 2 occasions, you first of all, if you want to look for group differences, you could use something like an ANOVA model. But if you just wanted to know if a measurement at time 2 was different from time 1, you can just use a paired t-test. Which is the code for which is we've gone over in ANOVA week. So you would just do a paired t-test with time 1 and time 2, and it would compare, sometimes called a dependent samples t-test. It would compare the scores in time 1 with the scores in time 2, with the understanding that those scores were taken from the same person, and tell you whether or not there's a difference. So the paired t-test is in some ways our simplest longitudinal model, simple but effective. This is a little bit different. So at a repeated measures ANOVA means you have at least 3 measurements, and you want to know if there's change over time across the span of all 3 of those measurements. So to do this, we're going to look at some data on sleep. And we're going to try to wrap our head around how some of this works. So let's load this in. The data are called sleep-wide.dta, and I'm going to load this in and just call this data frame sleep. There it is. And then I'm going to do a glimpse of that data frame right here. So it's a pretty simple setup. I have 100 people, and these data come from Michael Mitchell's book. I think I mentioned that before, Data for the Behavioral Sciences. So this is essentially a 100 people who were selected to participate in a sleep study, and they were randomly asked to for 1 night per month they would record how many minutes they slept, and then do that for 3 months. And so the goal is, and there may have been some kind of intervention too, I'm not sure, but the goal is to see, are people sleeping consistently from month to month to month, and if not, perhaps examine why. So these scores are all minutes. So this person slept for 300 minutes, so that's like 5 hours and 3 minutes. 400 minutes would be like, divide by 60, 6 hours and 40 minutes. Beyond that, it's hard to do them in my head. So, but anyway, so that's the sleep data set. So let's pay attention to this, because this is a good example. So I'm going to click on sleep here to view it. So the data are in this format, what are called wide format. And there are 2 fundamental data structures that you need to keep straight anytime you do longitudinal data analysis. And those are wide format and long format. Okay, wide format and long format. When we talk about data for a cross-sectional analysis, we actually don't need to worry about that as much, because we are essentially have 1 line per person, 1 observation per person, and we don't need to contend with the fact that we have repeated measures. But when you have repeated measures, it becomes more of an issue. So you have to either store the data in wide format or long format. So this is what wide format looks like. So each person gets 1 line in the data set. We have 100 lines. And notice we've recorded sleep 1 is the person's sleep in month 1, month 2, month 3. So person 1 slept for 300 minutes in month 1, 349 minutes in month 2, and 382 minutes in month 3, right? Now that's not the whole month, right? That's one randomly selected day out of the month. So wide format is really efficient. It's only 100 rows, and all that information is just stored in the columns, all that information about the person. This kind of setup is often really good for doing descriptive statistics, sometimes for doing plots and things like that. It's really, really, really useful. Unfortunately, for most of the modeling techniques that we use, including repeated measures ANOVA, unless we're talking about something called latent growth curve analysis, which goes beyond what we're going to talk about here, the data actually need to be in long format. In other words, one observation per line, repeated lines per person. So person 1 here had 3 observations. They actually would need 3 lines in long format. So this data set would actually be 300 rows long instead of 100 rows long, because we actually have 300 individual moments of measurement. So that's something to keep in mind, and I'm going to teach you some techniques for how to manipulate data from wide to long and then long to wide again. Again, if you do any kind of longitudinal data analysis, this is really important. So we'll run a quick summary on this data just to get an overall sense of what's happening. And again, this is easier in wide format because you get a summary of the average sleep in month 1 for your sample, sleep 2 in month 3. So in month 1, the average sleep was 348 minutes. So that's like 5 hours, 48 minutes. In month 2, it was a little over 6 hours. 360 minutes would be 6 hours. So there was some bump between sleep 1 and sleep 2. And then in month 3, it was about the same, 367 minutes. So it looks like we might have some change. The key is that change statistically significant and also practically significant, right? Does an increase of 20-some minutes really make a big difference? And is it statistically significant? All right, so let's learn a little bit about data management here to figure out how to handle this. The key to changing data from wide to long is a function from the dplyr package called pivot longer. Pivot longer. To do the reverse, we're going to learn about pivot wider, but first we're going to make pivot longer. So it's actually really not too bad. So here we say we want to create a new data frame called sleep.long, and that is going to be a function of first starting with sleep, our original data, and then using that pipe operator, we're going to pivot longer, and then a little decimal point just saying keep looking back up here at this original data sleep. And then there are a few commands we need to put in. First of all, the columns that we want to pivot all start with sleep, because we want to pivot sleep 1, sleep 2, and sleep 3. We don't need to pivot ID. ID is just going to repeat itself over time. Names 2 is going to go to month. So I'm going to have month 1, month 2, month 3. The values themselves, which are the actual scores in the data frame, are going to go to a new data variable that I'm creating just called sleep. And there's a prefix on the front of this called sleep. So that just means it's going to ignore this. And it's going to create a new variable called month, and that's going to be either 1, 2, or 3 for each person. And then a new variable called sleep, which is going to record the sleep for each person in that group. Okay? And then we're going to glimpse this new data set. I know this might seem super confusing the first time we do it, but I promise it's going to make sense once you look at it. So notice when we glimpse this, we now have a new data frame that is 300 rows and only 3 columns. Before, we had a data frame that was 4 columns and 100 rows. So let's look at sleep.long. Here it is. And notice this is now in long format. Here's person 1. Person 1, month 1, 300 minutes of sleep. Person 1, month 2, 349 minutes of sleep. Person 1, month 3, 382 minutes of sleep, and so on and so forth. So now we have a kind of stacked long data set that keeps track of month and keeps track of sleep. This is typically the format that we need the data in when we're going to do longitudinal data analysis, okay? Now, hypothetically, if you have a wide data set, you can also shape it back, or a long data set, you can also shape it back, kind of doing the reverse using this command, pivot wider, pivot wider. And here's the setup for that one. So we've got sleep.wide, so we're undoing what we did before. We actually don't have to because we have this variable sleep, or this data set sleep, but I'm just showing you. And it's going to start with sleep long, and then we're going to pivot wider, so we're going to go from long to wide again. The ID column, in this case, is ID. That's the one that doesn't change. The names are coming from month, and that's month 1, month 2, month 3. The values are coming from the variable sleep, and the prefix we're going to put on this thing is sleep. And just like that, famous last words, right? Just like that, we have our wide data set back again. So this sleep.wide is identical to the original data frame sleep, which is pretty cool. So very useful little technique here for how to work with long and wide data. And like I said, I like to actually keep both on hand. I like to have a long version and a wide version of the data frame because certain techniques are easier with one compared to the other. All right, so I also think it's a nice idea. We know descriptively that the data have shown some change from month 1 to month 2, not so much from month 2 to 2 to 3. But we can also visualize this. So here's, again, our friend ggplot. And we're going to learn a new ggplot geome this week. It's geome density. And a density plot is kind of a smoothed curve that is useful when you have lots of little discrete measurements like you have with sleep. You know, you have someone who slept 305 minutes, but then somebody else who slept 308 minutes. And so this can be a nice way to do that. And so that's what, here we have ggplot. Sleep is our data frame that we're going to use. We could also use sleep, let's see, sleep wide is what we're using here. This is the wide version of the data set. I have to keep it separate. Here is our x variable is sleep 1, so this is our plot for month 1. Geome density is what we're drawing. And then I've gotten a little fancy here. I've added a normal distribution to this just to compare my observed distribution to a normal distribution. You don't always have to do this, but and so that's what this stat function does. And this says to create a normal curve from an n of 100. And then this is my theoretical distribution. I just got these values, this mean and standard deviation, roughly from up here when we did the summaries. And I just kind of eyeballed it. It doesn't have to be super exact, just to give you an idea of how this compares. And then I add some labels using the labs function. And so there's a nice graph of our sleep in month 1. And the dashed red line is the normal distribution. So this actually doesn't look too bad. Maybe a little bit of a right skew, but otherwise it's not too bad. So that's the month 1. We can do the same thing for month 2. All I've changed here, I've adjusted the distribution. The mean is now 370 instead of 350 because it went up a little bit. And now I'm plotting sleep 2 instead of sleep 1. So this is month 2 sleep. Looks pretty good. Again, kind of a weird little distribution there, but not too bad. And then this is month 3. So here again is month 3. Oops, I had an error there. I got to make that month 3. Save that. And then I've got that. The distribution is still about the same. The mean is the same. The standard deviation. So I plot this. And there we go. So there's my distribution for month 3. It looks pretty similar, maybe a little bit different in month 3. Okay, so that gives me a nice plot just visually to see if things are reasonably normally distributed in each month. You can also do this automatically with the long form of the data set. Now this is getting a little fancy, but you can make a plot of all 3 months together. So we're using the long data set here, sleep.long, and x here is sleep. And we are faceting. Facet is a tool for splitting data out and doing separate plots according to another variable. And so we're faceting by month. So we're going to have a month 1 plot, a month 2 plot, and a month 3 plot. And this is fancy stuff, but what I like about this is you can see the shape, how the shape of the distribution changes as you move from month 1, 2, 3. You can see that distribution literally move to the right as more people are getting more sleep. And we can even, if you click this window, it'll pop open into a bigger window. And you can even see that more clearly. So isn't that cool? So yeah, so it's pretty heavily right skewed in month 1. And then you can kind of actually see that distribution move from left to right as people get slightly more sleep each time. So kind of a cool thing, just another thing you can try. We can also get descriptive statistics by month. So now we're getting into the code that is specific to the repeated measures ANOVA. And our two friends for the repeated measures ANOVA are first the rstatics package, if you don't have that one, and the ggpub-r. That's used for some of the assumptions, assessing some of the assumptions. So you want to download those if you don't have them. Let's see. Oh, I'm getting some kind of a error here. Let's see. Version check namespace. Broom is already loaded, but Broom is required. Let's try reloading Broom. Let's see here. Stand by and I will troubleshoot. Okay, and we're back. Sometimes, yeah. So even I have to battle with R sometimes too. What I realized was I had updated my packages, which you can update, by the way, just by clicking here, update, and then you can select select all and update. But when you do that, sometimes they don't talk very well with each other, and you kind of have to restart R and rerun everything. So that's basically what I did over that little break, which hopefully you didn't notice very much. Anyway, so I've now loaded in the rstatics package and the ggpub-r packages, and I want to do some descriptive statistics of sleep by month. And this is just a cool tool that you can use with the rstatics package. You can group by month. So this is now using the long data, because when you model, you actually need to use the long data. So this is using the long data. You can arrange by month, and then you can get summary stats for this variable sleep. And type just tells you what summary statistics you want. This is just the simple mean and standard deviation. So this isn't much different from, for example, doing summary. But the difference is if you do summary, you really need the data in wide format to compare. And so this is useful if you already have the data in long format. So we're basically getting the same information, and the standard deviation stays pretty consistent here, right at about 30. All right, so now how about that repeated measures ANOVA? So the command we use here is ANOVA test, ANOVA _test. This is not a base R function. This is a function from the rstatics package. The reason we do this is because in repeated measures ANOVA, we have a within identifier, we have repeated IDs, and we have a within measure of month, and we need a little bit more robust stat package to help estimate those things. So this is our first repeated measures ANOVA. The data are here, sleep.long. We have to use the long data. Our outcome is called sleep. WID is within ID, so that's the participant. Any within variables need to be listed here. In this case, it's just month. That's the only other variable in our model. We have ID, which is the person, and month. And then we get a summary of this. And because this is a little more sophisticated, you actually get 3 components out of this. So that's what the summary is telling you. You get the results, which are here. They're stored in something called ANOVA. You get a test of the assumptions called Mauchly's test for sphericity, and that's its own kind of little data frame. And then you get the sphericity corrections on your original result. Harumph, right? Lots of stuff. This is one of the things with ANOVA is you get lots of little extra kind of custom post hoc tests and things that you have to run. But let's just look at the results, and we can get the results by running this function get ANOVA table for sleep analysis of variance. So this part is very simple. What we have is, here is our repeated variable month, and the question that we are asking is, is there change in sleep across those 3 months? Or are all three of those essentially statistically equivalent after correcting for the individual and for month variation? And so here we get our test of that. We have some degrees of freedom here measures. We have our F statistic is 17. Our p-value is very small, 6.92 times 10 to the negative 8, so 0.00000 all the way out 6. And it is significant at the 0.05 level, so there's a little star there. So yes, we do see statistically significant change over time according to this month variable. We also get an effect size here, and I think that's a, I forget which one that is, omega maybe? Believe that's an effect size that's associated with that value. So all that, right, all that work kind of gets summarized down into one basic table. We also, though, and I talked about this in the lecture, whenever you do repeated measures ANOVA, you're usually worried about this sphericity assumption. In other words, the distributions themselves and the covariances between the distributions are probably not consistent. And so you probably should correct for that a little bit. And that is what is in this object called sphericity corrections. So if we just look at that, we just print that out, we get more information. So I know this looks like a lot, but basically what this gives you two corrections, sphericity corrections, and basically gives you adjusted p-values based on those corrections. And so typically when you see a repeated measures ANOVA, they will use one or both or more corrections. There are others. There's boxes, which is one that we use in Stata. In this case, GG is Greenhouse Geyser, and HF is Hohenfeld. These are two very sort of standard sphericity corrections. And what you're looking for is this thing here. This is the p-value, and this is the significance. So using the Greenhouse Geyser correction, we still have a significant p-value, and using the Hohenfeld correction, we still have a significant p-value. So it turns out, long story short, sphericity is not a big concern with this data set. And so we don't get very inconsistent results when we apply the corrections. If you have data that really violate that assumption pretty strongly, so you have data that are heavily skewed or not normal in shape and don't relate to each other in the same ways consistently, you can get big differences when you apply these corrections. And so you always want to check these because we know that that assumption is often violated. But in this case, we're actually in pretty good shape. We can also get some nice post hoc comparisons by month. There's a function called pairwise t-test also within the R-statics package. In the formula here, you just have to specify the outcome and the grouping variable. The data here are paired, and we're using a Bonferroni method. And then our data is sleep.long. This is not unlike the pair t-test that we ran in ANOVA week. But again, it gives you a nice kind of clean comparison. So here's month 1 compared to month 2. Month 1 minus month 2 is equal to -5. So that means that people slept about 5 minutes less on average in month 1 than they did in month 2. And about the same month 1 compared to month 3. Both of those are very significant. So here's the p and here's the adjusted p-value. And then here's the significance too if you want it. So these are highly significant comparisons. But the comparison between month 2 and month 3 was not significant. So basically we saw a big shift from month 1 to month 2, but then not much difference between month 2 and month 3. So that is the basics of the repeated measures ANOVA. So you got to have the data in long format. Once the data are in long format, you run the command. Then you look at the ANOVA results, you look at the corrections, and then you can do some comparisons by month too to see how things might be different. So the last part of this demonstration, we're going to talk about testing some of the assumptions that are cooked into repeated measures ANOVA. And there are a lot of these, so I'm just trying to distill it down to a few relatively simple tests that we can run to see whether or not our data meet the assumptions. Typically, we operate on the assumption that they don't, and we have to apply that correction. So that's just something to keep in mind. But the main assumptions, there are two: sphericity and multivariate normality. We already assume that sphericity has been violated, even if it hasn't, just because it so often is. And then multivariate normality. The MVN package in R does a nice job of testing a lot of these assumptions. And so first we're going to look at the process of testing univariate normality. And then we're going to look at multivariate normality. So this is how I recommend it. First, you look at the normality of individual variables, which would be sleep 1, sleep 2, sleep 3. And then once you've tested that, you can also look at the multivariate normal distribution, and those are actual additional statistical tests we need to look at. But typically, if you have a problem with one of the univariate distributions, it can cause problems with the multivariate. So here's a nice plot of all our variables. So this is what's called a QQ plot. What we're looking for here is that the dots, each one of these dots is equal to an observation. And as much as possible, we want these dots to adhere to this straight line. So deviations from this straight line, this XY line, indicate possible non-normality. Looks pretty good. We do get, so month 1 looks probably the best. Month 2, things start to tail off a little in month 3, but overall things don't look too terrible. Notice here that ID looks really weird. That's because ID is an ID variable and not a continuous variable, so we can ignore that one. But that would be an example of a non-normal distribution, definitely. Okay, so then sleep 2, so this actually runs a statistical test for that variable, and then we can print that out. So here, what I like, you do get very clear evidence. This is called the Shapiro-Wilk test, and it's testing the normality of each individual distribution. So test Shapiro-Wilk. So here's sleep 1, we're ignoring ID. Sleep 1, sleep 2, sleep 3, and sure enough, normality, yes, yes, yes. That's pretty good. And we have the p-value associated with that. So these distributions actually look pretty good across the board. So from a univariate perspective, it does look like things are pretty normally distributed. So now we can run a couple multivariate tests. So I'll show you 2. There's Mardia's and the Dornick-Hansen test. And these are composite tests that give you one p-value and one evaluation of whether or not the assumptions have been met. Basically, all you need to do here, create this object called sleep MVN, and then it's produced from sleep.wide, so the data have to be in wide format for all these checking of assumptions. The MVN test here that we asked for is DH for Dornick-Hansen. Down here it's Mardia, otherwise it's identical. And then we get our result. And so here it's interesting. Here's our single score result. Our p-value is very low, and we don't have multivariate normality. So even though we have univariate normality, we don't have multivariate normality, which is very common, because that's actually relating these distributions across time. And then same thing with Mardia's. Run that. According to Mardia's, we do. So we're getting kind of conflicting information about that. But that's not unusual. Again, these assumptions, what you'll find out with assumptions is that a lot of it is sort of shades of gray. And so you sort of use your adjustments, your greenhouse geyser adjustments or other adjustments as a way to argue that even small deviations from the assumptions aren't a big deal. And we'll talk about this more. Next week is all about statistical assumptions, so we'll dive in more about, or I think it's next week, maybe missing data, I can't remember, but one of those we'll talk specifically about ways you can argue that even if the data are not perfectly conforming to assumptions, that you're okay. The last one is the sphericity assumption, and that is actually was already calculated up above, so we'll just print it out. And here's the p-value here. So actually, sphericity, we're in good shape. The one that frequently is not significant, here's the p-value. We're okay. So to summarize, univariate normality looks good for each month. Multivariate normality is kind of a mixed bag. One test said no, one test said yes. Sphericity said the sphericity test looked fine. So overall, the assumptions here are in pretty good shape. I wouldn't be too worried about interpreting the results from this one. Okay, so to recap, we covered a lot here. We talked about repeated measures ANOVA. We talked about reshaping data from wide to long. We talked about assessing some of these assumptions. We really got into some of the nitty-gritty here to explore what was going on. And that's really the nature of repeated measures ANOVA. So do we have differences across time? Yes or no? A lot of other stuff is baked into that actual decision. So hopefully that makes sense. And I'm sure we'll be talking about this more in our weekly meeting. Good luck and have fun.